Hi, everyone. I'm Forrester Cole. I'm a software engineer in the machine perception group here in the Cambridge office. And machine perception is sort of the large organization that's responsible for sort of computer vision, machine hearing, computational photography, those sorts of topics. So this talk is going to be a bit technical, but hopefully, even if you don't get all the details, that's fine. It'll give you some flavor of the sort of work that we do in machine perception. And specifically, it's about depth prediction for people, which we're calling learning the depths of moving people by watching frozen people. And that'll become clear in a minute. So the basic setup, everybody's probably seen videos like this. You know, this is sort of a general, ordinary video. The camera's moving, people are moving. There's a lot of action going on. And what we want to be able to do is to create an image like this on the right. So there's if you're not used to looking at these sorts of images, that's a depth map. And what it's encoding is that each pixel value tells you the distance from the camera to that point in the scene. And in this case, it's encoded such that brighter is closer to the camera. So why might you want to do this? Well, it's actually useful for a lot of sort of things, especially in mobile. There are applications that you probably sort of have seen yourself. AR object insertion is one. You know, if you have a depth map of the scene, you sort of have a 3D geometry of the scene, you can put virtual objects in there. If you have that sort of information, you can also do synthetic defocus. So this is also known as portrait mode commonly, and it gives you sort of this nice bokeh effect. But there are many other applications for this: navigation, object tracking, rendering novel views, et cetera. It's sort of a basic problem in computer vision that's been worked on for a long time. And why isn't it already solved? So there are these devices, cameras, actually even small ones like these, that already measure depth in the scene. And so the depth camera works, for example, by shining infrared light out into the scene and measuring the reflectance, something like a radar. And the wide baseline stereo sort of has two cameras, and when you have two widely spaced views of the scene, you can do triangulation, and we'll see more of that in a moment. These all have their downsides. The depth cameras don't work very well at long range. They don't work outside. And stereo cameras can also be fooled depending on the scene at hand. But the bigger problem with these devices is that most people just don't have them. So they don't exist in a lot of cases. What does exist, and almost everyone probably in this room has one in their pocket, is a video camera on their cell phone. So why can't we do 3D from video? Well, this is, again, sort of thread in computer vision that's been worked on for a very long time. It's usually sort of referred to as simultaneous localization and mapping, or SLAM, or multi-view stereo. And if you have a scene, a video like this on the left here, where you have many views of a scene that's sort of a similar part of a scene where you have that it's rigid, nothing's moving, you can actually do a good job. You can get a nice 3D point cloud on the right. And we'll make use of this, but the problem for our current application is that it has to be stationary. So you require many different views of the same object from different angles, and the object can't move. And why is that? I mean, this is sort of a basic example of what happens in stereo. So imagine you've got two views of the same object. You've got correspondence on the point on the elbow. If you know the transformation between the cameras, you can triangulate and find the depth of that point. But if a person is moving, even if you have correspondence, if you know where the elbow is in each image, unless you know the motion of the person, you won't be able to you'll find you have an error when you triangulate those 2 points. You'll get the wrong depth. So this makes it difficult to use multiple frames of a video when they're moving objects. So what can we do? Well, in desperation, we can look at single view depth prediction. So this is sort of like the most kind of limited input case you can imagine for looking at this problem. You just have an image, a photograph, and you have some method that produces the depth map. That's the picture below. Again, so sort of yellow is kind of closer to the camera, dark is further from the camera. Of course, this has the well-known problem that when you project into an image, you destroy the information in the third dimension of the scene, and it's the case that an infinite number of shapes actually can project to any given photograph. So work in this field has also a very long history, and it's all been about trying to come up with prior knowledge, basically, and this is where the ML is going to come in. We need some kind of prior knowledge that tells us what sort of shapes in the world are likely and what are unlikely, because there's a whole space of shapes that this train could have a whole space of shapes, but really only one of them is actually very likely. This is potentially the oldest problem. I think it's the oldest problem in computer vision. It goes back to the 60s, and back when computers were fairly limited, the approach in this work, the blocks world work, was to imagine that the scene is composed of small geometric primitives, like triangular solids or rectangular solids, and the computer has a library of these things, and it tries to sort of fit them to this scene. And this is obviously limited. So in the years following that work, people tried to expand the sort of heuristics that you could apply. They expanded how you might fit shapes to photographs, might find vanishing points, this sort of thing. None of this ever really worked all that well, to be honest. But now, these days, with the advent of sort of supervised deep learning, things are starting to work as long as you have the data. So basically now it's just a straight up supervision task. You have a photograph, you've got depth captured by a depth camera or LiDAR or something we'll see in a minute, and you train an ML model to give you back that depth when it sees the picture. And these are starting to work pretty well, actually. So nowadays we have lots of data. We have multi-view supervision. We have different types of supervision. So we have video supervision, LiDAR, et cetera. And you're starting to get some good results here. But of course, it's all about the training data, right? And for these types of tasks, it's actually kind of hard to get training data. So there's a few data sets that are made up out of LiDAR. If you guys are familiar, LiDAR is the laser rangefinder that you find on self-driving cars. And these devices are sort of expensive and difficult to set up, so they essentially exist on cars and vehicles. And you never see any data for interior scenes using LiDAR, probably. Interior scenes, you can use a depth camera. This is the Microsoft Kinect, or there's a whole range of these devices. But again, like this is a special device. You have to go out and you have to actually actively collect this sort of data. And there just aren't that many of these devices in the world. Another thing that ML practitioners like to do is like to ask people, right? If people are already good at this task, people could tell us what the training data is that we need. It's too much work to ask a person to sort of fill in a whole depth map, though. So instead of, one thing you can do is you can ask a person which of these 2 points is further from the other. Like, given a pair of points, which one is further than the other? And then you extrapolate from that. But the upshot is that this is kind of limited, right? The direct real-world training data for depth prediction just doesn't exist that much. So we can work a little harder and go to different sources of data. So here's a very large source of data is images on the internet. If I go to Flickr and I search for Colosseum, right, I get a ton of photos of the Colosseum. And using some of those SLAM and MVS techniques that I sort of briefly mentioned earlier, we collect a bunch of those photos and we triangulate them, and you can actually get hopefully it's playing, yeah, a pretty nice and accurate point cloud of the Colosseum, just out of casual images that you captured on the internet. So this was some of our collaborators in this work did this on a large scale. Sorry, and then you can texture it. You can texture it with those photographs too. You get a pretty nice model out of that. Some of these our collaborators did this on a large scale. They went to, grabbed, say, pictures of 200 landmarks in the world and ran these multi-view stereo approaches on them. And what you get out are images that look like this. So now we actually have a depth map for these buildings. You'll note that the map itself is sort of noisy. It's not complete. This is actually fine for training neural networks. But more to the point, these are images of sort of well-known places. They have a lot of images of. You can actually find a ton of images of the Forum in Rome on the internet. So this works pretty well. And now you have your training pairs, and you train a network. So now you're seeing is just the output of a network that's been trained on to take the top row and turn it into the bottom row. And because of the way that CNNs work, they actually do a really nice job of filling in noise, ignoring noise and filling in holes, and you get a pretty good result out of this. So great, we've just sort of manufactured training data from stuff that wasn't training data, it wasn't captured as training data, right? People took these photos of all these places, and now we've turned them into depth supervision for training a network. So that's progress. So what's the problem? Well, we'd like to have depth for people, and people don't show up in these images. And basically, it's not because somehow the shape of a person is tough for multi-view stereo to capture. You can find depth maps of statues here, like on the top row. And that's just because this statue has been out there for a long time. A lot of people have come around, taken photos of this statue from different angles, and they've uploaded those photos to the internet. So we actually get a pretty good result for that. Now, with these folks down at the bottom, no one sort of at the exact same instant took a photo of them from a different angle and uploaded that photo of them to the internet. So our reconstruction is just missing those people. Like, there's just no data there. And what we really like to do, in some sense, is sort of turn these people into statues, right? Like, we want to be able to capture a lot of views of them without them moving, which is tough for people to do, and you're never going to do it, except, of course, that the internet is a crazy and wonderful thing, and this already exists. So I don't know how many people are, actually I'm curious, raise your hand if you ever heard of the Mannequin challenge before. Okay, actually a good number, all right. So around maybe 2016, this became a very popular thing to do on the internet where, you would tell everyone, okay, everybody freeze, and hold that pose. And then someone else would take their mobile camera and walk around the scene and film people as if they were mannequins. And they got the whole concert hall to do this, which is kind of amusing. It's a little creepy, yeah. It's like YouTube is this giant thing, and like if you look on YouTube for anything, you're probably going to find something, an example of that thing, which is kind of the lesson of this talk. So now you can probably see where this is going. It's actually really great for us. So we can go and we can capture 2,000, so like a couple thousand of these videos. They're very diverse. There's a lot of people that done different things. They're different people. They're people outside. They're people inside. And because they're stationary, now we get depth. So we can actually run multi-view stereo on these videos, and there's data there where the people are, where there wasn't data before. So that's kind of, now you've got the talk, right? This is basically, once you have this training data, you can do a straightforward sort of supervised learning task. You have the image on the left, and you want to create a network that's going to give you the values on the right. Same as we did before with the landmarks, the Roman Forum and so on. And this is just like sort of the most basic nowadays supervised learning task for regression, where, again, the sort of nice point about this is because you only apply your loss at the pixels where there is data. So multi-view stereo doesn't work all the time. It gives you data at a lot of pixels, but not all of them. But it's actually fine, because the network, due to the properties of convolutional neural networks, doesn't really care. Like, if you apply the loss at just the valid pixels, you'll still get a network that produces a full dense output like this. And so let's look at some results of that. It actually works, it works pretty well. So this is now a data set that we use for testing. It's test data where they've actually taken a depth camera out and sort of gotten ground truth. But we're not using that here. We're just feeding the RGB input on the left into the network, and you get something looking like the ground truth depth map. There are errors here, which I'm going to talk about in a minute. But just to say, this is what you do this is the result you get if you do the very sort of most straightforward thing with our data. But you can be a little more clever, and we did a bit more extra work to improve the algorithm, and that got us some actually qualitatively nicely improved results. So I'll talk about what this is in a moment, but the full model that we actually use has some nice features. It captures like the corner of this table. It gets the person's hand a little better. So what's the full model? Well, we have more information, right? Like this is not, we have a video, we actually have multiple frames, and furthermore, we have camera positions. So we have the track of the camera through space. Wow, is it going quickly? Okay, I'll slow down a little bit. And you can get this either through running SLAM, the way we did, or also AR Core, AR Kit. These toolkits for augmented reality on phones also give you that, at least a decent measure of what that camera position is in space by looking at the scene. How do we apply this? The insight that we applied here was to use the multiple frames to create kind of a, not a great depth map, do a lightweight version of multi-view stereo, basically, and get what we're going to call like a pseudo-depth map. So you run optical flow, and this is sort of another network that finds correspondences between the images along, each pixel has a vector, basically. That's what sort of optical flow is a correspondence between two images. Once you have that, and you also have the camera positions, you can make a depth map. But, of course, as we saw before, triangulating in this way for moving people isn't going to work very well. So we actually go ahead and we just cut out people. So this is the thing that we're going to feed to our network, is this sort of pseudo-depth map that has valid, estimates of the depth that are going to be somewhat inaccurate, but a decent place to start at places that we think are not moving. And for this work, we're just assuming that anything that's not a person is not moving. So now our full model looks like this. You have color image, you have masks of the people in the scene, and you have this pseudo-depth map that we computed from flow. And again, the back end of the network looks basically the same. That is, it's a regression network, produces pixels, and the loss is the same. The loss is that the multi-view stereo depth. So here's some results comparing with what was sort of state-of-the-art on this task. And I'll talk about a little bit why the other results look so questionable. But ours is in the lower right. And you can see that you get pretty nice clean outlines of people. There are definitely some artifacts remaining, but overall, compared to the previous methods that are working on a similar video, it looks pretty clean. Here's another example. I'll just play that again. All right, and I just want to make every time I show this, I feel kind of bad because like the method like DORN, for example, here is actually, this is a state-of-the-art method. This is a good method. It just is not working very well here, and I'll show you. This is sort of a lesson about data in ML again. This is DORN on the actually original test data that method was developed for. So there are no people, right? There's no people in this scene. And it works pretty nicely, actually. These are good results. This method had sort of the top-ranked results on the kitty benchmark for a while. And what you're seeing here is just a network that's got a good architecture, but is totally confused because it just hasn't seen that sort of input before. That's the upper left, DORN there. I'll show you a few more results, just to show the sort of the versatility of it. Let's play that one more time. All right, what can you do with this thing? One thing we can go back to, we can sort of make a portrait mode style effect, a synthetic defocus effect for video now. Play this one. There's a focus pull kind of towards the people, focus pull to the background and back to the subject in the front. Play that one more time. That's one of the effects that are sort of nice to have on a mobile phone. We can do object insertion. We didn't push this too far yet because there are, as you sort of see from this example, still some artifacts that would make it not a great result for a product. But you can see the beginnings of a way to sort of insert synthetic objects into the scene. And another one you can do is sort of synthesize new views. So you have primitive geometry of the scene, and you can now kind of move the camera around a little bit to get some different views of the video while it's playing. And one last application I'll talk about is this idea of sort of inpainting based on the depth maps. This is nothing sort of amazing in terms of the application, but just to show if I remove these people, normally there'd be a hole here. But because I have a video and I have geometry of that video, I can actually reproject from neighboring frames, and I can fill in those holes with real data. Like, this is not sort of synthesized from a GAN or anything. This is, RGB from other frames of the video reprojected correctly because we know what the geometry of the scene is. So what are the takeaways? One is data can be found in surprising places. And maybe like the more general lesson is like, if it's hard to find or to create labeled data for a particular task, that's not necessarily a reason to give up. I mean, you can go and you just need to be a little more clever. You have to find a way to create that data from stuff that's already lying around. And another thing is that even when you do that, though, data isn't the end of the story. Clever algorithms do matter, so we were able to get a 50% improvement in our numbers by just working a little harder to design the prediction algorithm of the network itself. So future work, I guess you probably have noticed that these videos flicker a bit, and I've cheated a little bit by showing the depth maps and not like point clouds of this actual geometry in space, because you'd see that this thing is actually shaking a fair amount. So this is something I think all these methods suffer from, and we have to do a bit more algorithmic work to figure out how to make these results more stable over time. If you want to play around with this, there's the code and for inference, and the models are available online. We also have the data, the camera tracks and the video IDs that we use to create the Mannequin Challenge data set online. So you can download it and play around. And that's it. Thank you to my collaborators that worked on this with me, especially Jung-Chi here, who did most of the work. And thank you for listening.